Hi again for you chemistry students. So we're starting a brand new unit today on equilibrium, which is our fourth unit. And from the videos I've had you watch, you've gained an appreciation for what equilibrium is. We're going to focus on chemical equilibrium. However, it does happen with physical processes as well, such as changing state. Like if you have a wet bathing suit in a plastic bag, it is going to be evaporating and condensing simultaneously, and your bathing suit will remain wet. Also happens with the physical process dissolving, where crystals can be dissolving and recrystallizing at the same time. We will look at that a little more later. But for now, we're going to focus on chemical reactions. And so we're saying not all chemical reactions go to completion. This was introduced in grade 11 as one of our possible sources of why percent yield might be low in a reaction, because it starts reversing and it is making reactants more than products, for instance. Now, it's very important that for equilibrium to be reached, you must have a closed system, which means the container cannot allow matter to enter or exit, only energy. And when we're at dynamic equilibrium, which is what we often call it, the word dynamic means things actually are always changing. But equilibrium is stating that there is something very important that is the same, and that is the rate, and I'm just going to write a little subscript here, of the forward reaction, okay, is going to be equal to the rate of the reverse reaction. So we just finished up our unit on rate. So that is what is happening at equilibrium, that the rates are equal. The other thing that happens at equilibrium is that all concentrations are constant. So I'm not going to say they're equal to anything. I'm just going to say they're not changing anymore. However, we're constantly doing stuff. So stuff is changing. We're going forwards, we're going backwards, but because the rates are equal, we end up not seeing a change in our concentration anymore. So this is reflected nicely on these graphs. These are concentration graphs. Notice reactants would always decrease at first because they're going to get used up. Products will always increase. And rate, when we've decided with this dotted line that equilibrium has begun, the concentrations don't change anymore. Okay, so we can see in both of these graphs that there becomes a point when we're at equilibrium when that happens. Now, the difference between these two graphs is in the first one, reactants are being used up, products are being produced, but when all is said and done, there are, a greater concentration of products compared to reactants. So we would call this particular reaction product favored. And that is usually what we're going for. We're trying to make more products. Chemists spend their entire careers looking for ways to get the most product they can out of reactions. Now, in this case, we ended up with more reactants. So this is going to be called reactant favored. Okay, now let's look at this final graph, which is entirely different axes. Well, we still have time on the bottom, but now we're looking at rate. So just another way of thinking about it, that the forward rate, so say things are making products very quickly at first, that rate is going to get slower and slower, because what we've just learned in the rate unit is that as concentration decreases, rate will be slower because you're going to have less collisions. So the forward rate will get slow, but because you're now making products, the rate of the reverse reaction where the products are going to react to make reactants, sounds kind of weird, it's going to get faster because its concentration is getting larger and therefore collisions can happen. But at some point when we hit equilibrium, this is where we're saying the forward rate and the reverse rate are going to be the same. Okay. So as I said, we're going to focus on chemical reaction equilibriums. Okay. So just some definitions. Forward reactions are going to go from left to right. They make products. They're what we're used to thinking about. In grade 11, we didn't talk about reverse reactions. We just thought everything went forward and went right to the end, which in the ideal world would happen. Now, another little point is, well, first of all, notice the funny arrow when you have an equilibrium reaction. Sometimes people will write it just literally with 2 arrows like that as well, just something to show that it is going forward and reverse. And here I have a reaction where we have sulfur dioxide and oxygen producing sulfur trioxide, but it's reversible. So there's no reason why I can't write it like this. So I've got what was the products now as reactants. It does not matter how the reaction is written on paper. When it gets to its equilibrium state, it would be the same either way. So that is not going to have any effect. Okay, so we like to quantize things sometimes in chemistry. So with equilibrium, the fact that the reaction is proceeding backwards at the same time as it's going forwards, clearly we're not going to get 100% yield. And that is why in grade 11 we talked about using that as a reason you don't get 100% yield. As we said, some reactions are reversible. So percent yield, percent reaction, you remember, is the actual product you get divided by theoretically what could you have got, when you did your stoichiometry calculation. So actual is, in the lab or the factory. Okay. So if you have no reaction happen at all, then your percent reaction is basically going to be 0. Nothing happened. If reactants are favored, then we're saying that this is a less than 50% reaction. So this is probably not desirable in a factory or lab situation because we usually want to get as much product as we can. If you are greater than 50%, and go, it's product favored. Now, if your percent reaction ends up being exactly 50%, then you're just right in the middle. It's not favoring either. You're getting half reactants, half products. Now, a quantitative reaction where you're having 99 to 100% reaction, this is like what we basically thought everything did back in grade 9, 10, and 11. So kind of like a grade 11 assumption when we would do stoichiometry calculations, we just always assumed that the reaction was going, all the way to the end. But now we know otherwise. Okay, so because some reactions do not just proceed right to the end and make, great amounts of product, our calculations become more complex now. We can't do stoichiometry quite the same way we were in grade 11 for these particular reactions. So we're going to use something called a Rice table to help organize our information. Now, some textbooks and videos, even a video I had you watch today, call them ICE tables or ICE boxes. I like Rice just because the R stands for reaction. So this is a place where you actually write your chemical reaction. And then everything else is all about concentrations. So concentrations in moles per liter, okay? So the initial concentration, so when you start off your reactants, what are your initial concentrations of those reactants? Then we're going to look at, well, how do those concentrations change as the reaction proceeds? So that is C for change. And finally, what are the concentrations of all your substances when you have reached equilibrium? And we know at that point the concentrations aren't going to change anymore, but products might be much bigger than reactants or vice versa. All right, so of course the best way to do this is with some examples. So always set up a rice table, highly recommended. And I have just filled this in already to save a little bit of time. So here's our reaction, hydrogen and fluorine gas making hydrogen fluoride. So I've told you the size of the container. It's a 2-liter container, and you have 2 moles of hydrogen and 4 moles of fluorine. So for initial, this absolutely has to be concentration. Okay, so we need to do a little calculation off to the side. If you remember from grade 11, concentration is moles divided by volume. So if we're doing hydrogen first, what do we got here? 2 moles of hydrogen divided by a 2-liter container equals 1.0 moles per liter of hydrogen. So that is initially what we're starting off with. Okay. Now if we do the same for fluorine, we've got, so for fluorine, we've got 4 moles. And again, we're dividing by the 2-liter container, so 2 moles per liter. With a lot of these questions, you'll just be able to do that in your head, but the key is that you don't forget to do it, because it absolutely has to be concentrations that you work with in a rice table. Okay, so initially we have 1 mole per liter of hydrogen, and initially we have 2 moles per liter of fluorine in this closed container. Now at equilibrium, the concentration of hydrogen is 0.24 moles per liter, and they want you to calculate all the equilibrium concentrations. So we're going to use this down here at the end in order to solve our question here. So before we start, if that's what we put in the container, over here for the product, you can say that there is just 0. So at the beginning, you didn't have any product. Now here's the key. How much does stuff change by? Well, we don't know, but we do know for every 1 mole of hydrogen, it's going to react with 1 mole of fluorine and make 2 moles of hydrogen fluoride. So we can say that this changes by minus 1x. Okay, this is also going to go down by minus 1x, and this is going to go up by 2 times x. We don't know what x is, but we do know you're going to get double. So these numbers, the 1, 1, 2, are coming from the coefficients of our balanced equation. So imaginary 1, 2. Okay. Now at equilibrium, we're going to work it out by saying, okay, we had an initial value and we know how much it changed by. So fill in, just put these together. So 1 subtract x. Here we've got 2 subtract x. And here we have 0 plus 2x, which again is kind of pointless to write the 0, but just for an example. Now, that's great. We have a whole bunch of equations, but if you remember, we were actually told a value here. 0.24 moles per liter was the concentration of hydrogen at equilibrium. So now you can fill that in. And then you can do a little bit of algebra and say negative x, and then we're going to subtract this, is going to we're going to subtract 1 from 0.24, so we're going to have negative 0.76, and then multiply everything by plus 1, so 0.76 moles per liter. So that is the concentration, that is the value of x, I should say. So now if we fill that in, okay, so we're going to sub into here, if we say 2 moles per liter, subtract 0.76 moles per liter, is going to give us 1.24 moles per liter, and that is equal to fluorine's concentration. Remember, square brackets tells you concentration. Okay, so there's one of our answers because it said find out how much of everything you have at equilibrium. Okay, so for HF, we just have 2x, or 2 times 0.76 moles per liter, which is going to be 1.52 moles per liter, which is HF concentration. Okay, now so these are all actual amounts that we've got in the real lab. Okay, so this is actual yield. So we could actually do a calculation and figure out, what our percent yield was for this reaction. And it wouldn't matter which, initial reactant you use to figure out the product, but the fact that at first we had, 1 mole per liter, if you looked here, for every 1 mole you were supposed to get 2. So technically, theoretically, we should have got 2 moles per liter, but we only got 1.52. And if you take 1.52 divided by 2, that would be a 76% reaction. So the percent yield is 76%, which does tell us we're product favored, but not 100%. Okay, now for the second question, I wanted to give you one where you have to maybe get a little bit of information from a graph. So this is a concentration time graph. I think that got cut off. Okay. Moles per decimeter is the same as moles per liter. Okay. So this is a reaction between A, B, and C. And we haven't been given the actual reaction, but just given that it's written ABC, we'll just assume that there's one of each. And from a graph like this, the way you can tell who the reactants are and who the product is reactants are going to go down at first because they're going to be getting consumed. So it's definitely A plus B that is making C as a product. Okay. Now we can read right from the graph quite easily what our starting concentrations are. So A is 4.0 moles per liter. B, I would say, is 3.5 moles per liter. And C, of course, is 0, which we would expect. Okay. So how much are things going to change by? Well, everything's 1, 1, 1. So we're going to have minus x, and plus x. So on the equilibrium line, we have 4 subtract x, 3.5 subtract x, and just x, 0 plus x. So question says, if at equilibrium the concentration of B is 2 moles per liter, and if we look here, at equilibrium, you can kind of tell that's lined up with 2, but we're just saying it is 2. So here we've been told that this equals 2 moles per liter. So once again, we can do some algebra. So negative x, and we're going to subtract that, is going to be negative 1.5, or x is 1.5 moles per liter. So once we've solved that, now we're going to sub. So concentration of C is 1.5 moles per liter. And we're going to sub over here. 4.0 minus 1.5 is 2.5 moles per liter, which is concentration of A. Now, we could have also read these off the graph. I just wanted to kind of give you an example of how you can use a graph. It was a little harder to see, but yeah, it's about 2.5, looks good. And C, if you extrapolate over, looks like it's around 1.5. Okay, that is it for today. Thank you.